Hello everyone, welcome back to Computer Science 354, Machine Organization and Programming. In this next piece, we're going to be looking at how computers work on the inside. Alright, so just a quick high-level overview of the entire course all at once. The next weeks are going to be broken down into three basic sections. The first one is going to be about C programming. The second half of this course is going to be more or less focused on assembly programming, very low-level stuff. Code that does one instruction at a time. And finally, we'll talk about some system topics. And some examples of those would be things like virtual memory, caching, communication and interrupts, dynamic memory allocation, operating systems. And I've got some blanks here. If you guys have some topics that you'd love to hear me talk about, send me an email. Let me know what you're interested in. Take a look at the textbooks. Those back couple of chapters have a lot of stuff that I've got to choose some things, and I don't have time to do all of it. All right, so there's the course overview. Now let's start digging into today's topic. First, I'm going to spend some time to talk a little bit about how computers work. So just the really obvious things. I've got a big box over here on my desk, or I've got a laptop. That's hardware. I'm also running some code. It could be a web browser or a piece of code that I wrote, or a PowerPoint, something. I've got a program I'm running. In between that, we have software systems. And this is going to fall into, here, I made some slides. So word processing, web browsing, C programs, PowerPoint, things like that would be applications. Under software systems, this is going to be our operating system, things that connect an application program that we care about running to the computer hardware so it does stuff. So Windows, Linux, also any sort of hardware driver like your graphics card. NVIDIA tells me every single week that it's got a new update for my graphics card. Things like that. That would be a software system. And finally, the hardware. Three major pieces we'll be talking about today are the CPU, the processor, the memory, which is also known as RAM, and the hard disk or solid-state drive, SSD. All right. So let's take a close look at what happens when we run a program. So here I've got just 3 lines out of a much larger C program called sum. All this program is going to do is take 2 numbers stored in variables and add them together and store that in a third variable. So as we run this code, I want to take a look at this from a very specific point of view, the von Neumann architecture. So this is a computer system described many years ago, maybe 1950s, where the model of the computer has a processor, the CPU, that does all of the logic and math operations, and it's got some memory. Those two are connected together. So a place to store the numbers and something that manipulates the numbers. Now, without input and output, this would be pretty worthless. So we're also going to be using input and output as part of the model we're looking at. And input and output could possibly be the same device, like a hard drive. I can input data into memory, manipulate on the CPU from a hard drive, and then I could save the results. But things like monitors, keyboards, mice, internet connection, all those would be inputs or outputs from this point of view. Okay, so I want to draw this same picture a little differently now. If you actually take the cover off your computer and look inside, you can see the memory chips, you can see the you can see the giant fan on top of the processor, and you can see your hard drives. So they're all connected. They're just pieces in the computer. So what I want to ask is just take a second and think about this. If I write this code, I opened up an editor, I type in all the lines, and then I save it. Where exactly does sum.c, that's the name of my file, where does that exist? Is it in the processor, the memory, or on the hard drive? All right. So make a commitment, make a decision, put your finger on one of those 3 boxes, and in 3, 2, 1, I'm going to click. There it is. It's actually stored on the hard disk. When I write a file and save it, that's going to go straight to the hard drive. The next thing that we do when we're going to run a program is we need to compile it. So the processor cannot deal with language like this. It can't say A equals 1, B equals 2, and actually understand what's going on. It only reads machine code, or binary code, the zeros and ones. So the process of turning this high-level code that's actually readable, hold on, where's my mouse pointer? Pointer options, arrow, visible. There we go. So we can turn this code into something the computer can read. We're going to use a compiler. You guys have likely seen this before if you took Java. Java has a compiler that generates bytecode that then runs on their Java interpreter. And this is just going to be binary at the end of it. In fact, this file, after we're done compiling, is also stored on the hard drive. Oh, that's the next slide. All right, so a couple of definitions. This code over here that I write in my text editor and save is the source code. The compiler that we'll be using is GCC. That's the compiler available on the Linux machines in the lab. That's an abbreviation for GNU C compiler. And GNU actually stands for GNU not Linux, not Unix. Misspoke there. GNU not Unix. So it's a recursive definition if you think about that a little bit, because this GNU also stands for GNU not Unix, and keep going forever. So anyway, this is just our C compiler. And this code, the binary code, is known as the executable. It's also called an object file or machine code. I'm going to use all three of those to mean the same thing. Okay, now this is the slide I was thinking of. This one right here. So the binary code in my sum file is also stored on the hard drive after the compiler is done with it. So check this out. My source code has the .c extension. When I compile it, it's just going to be sum without an extension. And in fact, on the Linux, if you list all of the contents of a directory, it'll have a little star because it's an executable. All right. In the computer, the motherboard, that really colorful, mine's black, I believe. They used to all be green. Just circuit board in the background that all of these things attached to have millions of little wires that connect everything together. All right, millions is an exaggeration, but lots of little wires all embedded in that circuit board that connect the processor to the memory to the hard disk. And in fact, if you look at typical hard disks, the newest flash drives are actually built right into the motherboard. But if you have like a mechanical hard disk, they're going to be off to the side with probably a SATA cable these days, connecting that hard drive to the motherboard. I don't have a screwdriver right here, otherwise I'd pull this apart and show you guys. All right, so the next thing we're going to do, after we compile the code, I'm looking up the top here. I've got my 3 arrows. This is the prompt, command prompt. When we run a computer program on a Linux machine, we need the // that tells me to use the program in the current directory, just in case I have more than one program called sum out there. And then I need the name of the program I'm running. So the first thing that happens when we start running this code is the operating system is actually going to run another piece of code, a program called the loader. And that's going to take this machine code and actually store it in memory on the RAM chips. And it's going to be divided into 2 sections. There's going to be a code section. So in this case, I just copied one line here. This is the part that's actually going to do something. So C is equal to A plus B. That's going to go in code. And we'll also have a data section where we're going to store all of the variables and the contents of those variables. Okay. So, all right. The loader is a program that the CPU runs that just moves data from the hard disk to the memory, so it's ready to go. All right. If we take a little deeper look at the processor, we're going to find that it also has some locations for memory. There's really only like 10 of these on a typical computer processor. And the one I've drawn here only has 3. So these registers are locations where we can store numbers. So the next thing that happens as we look at this, I've got A is equal to 1. We're going to copy that. Okay, let me rewind a little bit. When I'm looking at only this line in the red box, in order for my processor to execute this line, these numbers are stored in memory. It doesn't work with numbers in memory. It only works with numbers that are in registers. So the first thing it needs to do is actually go and grab A from memory. So this is going to be a load operation. So it's going to get the number 1 from the memory location where A is and stick it in a register. And in this case, I'm putting it in register 1. The next thing it's going to do, it needs to get this number B. So it goes to memory, grabs the 2 there, and stores that in another register. And finally, it can do this arithmetic operation, the addition, add those 2 numbers together, and store that in another register. It actually could be stored in one of the 2 we've already used. We're done with those once we get the sum. So, but in this case, I've stored it in register 3. And then finally, it needs to go back to C. This is the assignment operation. And so when the memory is transferred, or when the number is transferred from the processor to the memory, that's a store operation. So we're storing B. All right, so the CPU goes through this cycle, and each one of those steps was broken down into really 3 parts. So if I back up a second, this load operation for the first part would be, first thing it's going to do is fetch the instruction that says I need to load something. So fetch is going to be the first thing that happens. It's going to get an instruction from the memory. That's going to be from the code side of things. Then the next thing it's going to do is decode that. It needs to figure out what kind of instruction it is. So I'm going to have instructions that fetch, that store, that load, that store, that do math. It needs to figure out what kind of instruction we're looking at. And finally, it's going to execute that instruction. So if it's decided it's a load instruction, this is the part where it goes and grabs the number and sticks it into a register. If it's a math operation, that's where it's going to do the math and add the 2 numbers together and then stash that in another register. All right, and this is going to be just repeated in a loop endlessly. So as soon as it's done doing the first instruction, and as soon as it's done executing, it's going to go back and fetch the next instruction. It's going to figure out what it's supposed to do by decoding it. It's going to execute that instruction and then go back and get another instruction. It just does this forever. Okay, so the last thing I want to talk about in this first half of the lecture for today is what happens when we actually compile our code, the build process. After we're done writing the code, and I've stored that in a file, sum.c in this case for this program, and then I run the compiler to actually produce my machine code. The first thing that's actually, the compiler is a program. It's actually a series of 4 programs that are run by the CPU that manipulate the code from this file, transform it in a number of steps into my machine code at the other side. So it takes in the source file. The first thing that happens is the preprocessor is going to operate on my source file. This is going to go ahead and remove all the comments that the rest of the compiler doesn't need. If there's any preprocessor or compiler directives, like to include another file, actually the preprocessor is kind of its own little programming language, and we'll see a lot of pieces of this throughout the course. But it's going to go through and produce another file, and this typically has the .i extension for like intermediate code. And this is also known as the preprocessed source file. In the next section, like part 2 of the video, I'm going to go through and break down the build process into each of these 4 steps and just show you what these files look like after we're done preprocessing them. Okay, so the next thing that happens is the compiler proper. This is given the abbreviation CC1. The abbreviation for the preprocessor, CPP, stands for C preprocessor. Capital P right there. Okay, so yeah, the next thing that happens is the compiler proper. This is going to produce code that's actually written in assembly, which is mostly human readable. I'll be pulling up an example of this when we actually do the demonstration in part 2 of the video. The typical extension for this is .s, assembly, right there. It's the second letter. And this is going to be, I'll show you a demonstration in part 2 of the video, but this is generally human readable after you've had some experience learning it. It's not easy. Okay, the next thing that happens is the assembler will take this sum.s file and generate what's known as an object file, or more specifically a relocatable object file. And this is going to be machine code at this point. It's going to be in binary, so 1s and 0s. But it's not going to be the complete everything we need. If we've included anything from another library, the standard library, for example, then we'll still need one final step, the linker, abbreviated LD. The abbreviation actually comes from the fact that the linker and the loader used to be one component, and so the LD is stuck around as the abbreviation. But this is going to go and grab all of the object files, sum.o, or if I've got another I've included something else, like something from the standard library. It's going to go get the object code for that and merge them together to finally create the executable. And this is typically without an extension. No reason you couldn't put one on there, but typically without. And this is going to be binary code that's able to operate and do, pretty much run the entire program.